Okay, well, I would like to welcome everyone here, obviously for the talk by Peter, but before actually doing so, it's also a welcome to a new week, and a week in which the so-called SNA02 workshop, so it's kind of the statistical network and its applications are going to be central. So we're very pleased that together with Veronica sitting here and Patrick, we have put together a program, and the program consists basically of the very first 3 days to have a set of 2 talks, and they're often in the morning. Often is basically 2 out of 3. So today clearly it's in the afternoon, just to give people the opportunity to get here if they were coming locally. And then tomorrow it will actually be in the morning. If I remember, 10 to 11, and then 11:30 till 12:30. So if you've studied the program very well, but before last Friday there has been some changes. So just to let you know, today's talk is followed by tea break. So we have half an hour tea break, and then we have the second talk. And that then is then followed at 4 o'clock instead of 5 o'clock by the opening reception. So if you can immediately have booze at 4. So it's quite quickly. So everyone welcome, please join as well. So then on Thursday and Friday we have another opening session, in the sense that then we have the kind of the continuous workshop, which is a workshop associated with a publication in the Journal of Royal Statistical Society C, so Applied Statistics, and effectively the people that were selected for that particular publication are going to present their presentations together with some PhD students giving some short presentations on Thursday and Friday, and so then we also have the kind of public workshop, so we also expect about 40 participants, and then you see lots of names on the table lying there, and they will be all coming. They're not expected right now, they're all coming on Thursday and Friday. Good, so sorry to take the attention away at the beginning from Peter, but obviously Peter is giving a talk that maybe sounds very familiar, in the sense that if you were here last week and Frank gave a talk which was basically epidemics on network. Frank is here in the co-authors as well. It's now emerging epidemics on networks, and clearly there's relationships between the 2 talks, which is nice, and have them so close together. But Peter is actually right now, I think, what is it called, a docent, or is that kind of a nice name for it?
Yeah.
Professor at the Mathematical Institute, or there's a nice name for it in Swedish, which I can't pronounce. Department of Mathematics, as he called themselves, and the University of Stockholm. So we're looking forward to your talk, and thanks for being here.
Thank you. Thank you for letting me talk here and give me a good time, an hour to talk. That's really generous, and thankful for that. As said, Frank gave a talk recently on something very similar. I wasn't at that talk. I haven't seen the slides of the talk, but we discussed beforehand what was more or less going to be said. So I hope there is not too much overlap, and apart from that, I don't expect that everybody of you were here at Frank's talk, so I will try to explain as much as is needed to understand this talk. So I'm talking about emerging epidemics on networks. This is joint work with quite some authors. Frank is involved, Tom Britton, Pieter Trapman, Jean-Stéphane Dessin, and Jacobo Inga. It started as joint work with Tom and Pieter Trapman. Then we were at a workshop in Ohio in 2011, in Columbus, Ohio. And then Frank and Jean-Stéphane also joined in. We had some problems we couldn't solve, and they went around, so that was nice. Then I was talking to Katja Köhler in Duke University. I was there for a short visit and talking about what we were going to do, and her response was, "You're not going to hide this in some mathematics journal, are you?" So we decided that we might try to aim high. Well, in the end, we aimed a bit too high. No, don't worry about nothing more about that. But anyway, we cannot go with 5 mathematicians to write a paper for something like Nature or Science. So then Jacco Wallinga came in, who is at the Public Health Institute in the Netherlands, National Public Health Institute, and he gave us quite some insight in what is important from a public health perspective. So that's how this came about, and in the end, last week we heard that this paper is, well, now a couple of weeks ago we heard that it's accepted in the Journal of Royal Society interface. Last week the proofs went back to there. So, what is it all about? Now, if you have heard a talk about infectious disease epidemiology before, you probably have heard about the concept of R0. Or if you have seen one of those movies like Contagion or so, where even Hollywood explains what R0 is. So, R0 is really what all epidemiologists are interested in, and it's the number of individuals infected by a typical infected individual, whatever a typical infected individual might mean. So if you get infected, how many other individuals will you infect in expectation? So we can also define R0 as here, as we have a population of n individuals. We look at how many individuals are infected within k infection steps from the initial infected individual, if it's introduced by one infectious individual. Well, of course, we want to have a large population, so actually we define R0 for a sequence of epidemic models, and then we take the limit of n to infinity, and we hope that this limit exists. And then we look at how many individuals are infected in this large population limit after k generations. We take that to the power 1 over k, and we take k to infinity. Okay, so this is basically the basis of the base of the exponential growth. That's what R0 is. And here we define it in terms of expectations. You will later see that we go to branching process approximations, and then this limit exists in a more general sense. We don't have to talk about expectations. We have almost sure convergence of xk to the power 1 over k. So R0 is the asymptotic expectation of the offspring, or the number of children, in an approximating branching process, if that approximating branching process exists. And a large outbreak is only possible if and only if R0 is larger than 1. That you might know from branching processes. So R0 is really just the offspring mean of the branching process. Now, if you look at the epidemiological literature, I think in 99% of the models, this branching process approximation actually exists. That's not because it exists in reality, that's just because there we can do computations. So as I said, a large outbreak of an epidemic, and I will define more what kind of say more about what kind of epidemics I will talk about. It's possible if and only if R0 is larger than 1. Critical vaccination coverage is 1 minus 1 over R naught. So if you vaccinate a fraction of the population with this, or this fraction of the population in a nice way, then there is so-called herd immunity and a large outbreak is impossible. So the effective R naught becomes, gets below 1. And what is nice about R naught as well is if one knows all individual-based parameters, so what's the probability of infecting your neighbor or somebody else in the population, how long will you be infectious, what is the distribution of your infectious period. If you know all those things, then it's usually pretty straightforward to compute R naught. So because of those top two properties of R naught, that's why epidemiologists are so much interested in R naught. Another parameter is the Malthusian parameter, alpha. This is just the real-time variant of R naught. So remember, we define R naught as the number of newly infected individuals by one infected individual itself. So you don't care about when those infections take place, just by whom infected whom. Alpha is, or the Malthusian parameter, says how quick the exponential growth of an epidemic is in the early phase of the epidemic.
R0 is just infected directly or through the generation?
Yeah, it's direct infection. So it's the number of, in an approximating branch process, it would be the number of children of an individual, not the number of grandchildren and so on. So if somebody on average infects 1 or 2 individuals, then a large outbreak is possible. If it's on average a half, then something else happens, or it sticks to a small outbreak. So to say what alpha is, roughly this e to the minus alpha t times xnt, where xnt is the number of infected individuals at time t in a population of size n. This converges some sense, well, almost surely, if we first send n to infinity and then t to infinity, and we should couple the different epidemic models for different population size in some nice way to let this statement make sense. Now, what might be obvious from the interpretation, alpha is larger than 0 if and only if R naught is larger than 1. Remember that if R naught is larger than 1, then the epidemic grows, and only if alpha is larger than 0, this number of infected at time t grows in t. So this makes kind of sense. And the nice thing about alpha is that it's often relatively easy to estimate from data which are available during the emergent state of epidemic. However, if one knows all individual based parameters, so as before, how long is somebody infectious, what's the probability of infecting someone else in the population, you know all those things, then computing alpha in closed form is often hard, if not impossible. There are only a few special cases in which we can compute this alpha. So, being coming from probability theory, not too much into statistics, I never cared too much about alpha, and definitely not about estimation purposes or estimation problems. This I also wrote something in the first talk. I think I wrote this in the first talk I gave about this subject when I was still pretty confident that this relatively easy made sense. It's actually still pretty hard. But at least for me. But compared to estimating R0 from data, it's way easier.
Sorry.
Yeah.
I'm a little bit confused by some Malthusian. Is the size of the population, the overall size of the population, fixed?
So what we actually do is define it for a series of epidemics coupled in a nice way where the population size goes to infinity. Of course, in real life we only have one outbreak, we hope, in a finite sized population where we assume that the population size is large and that it's large enough to show this limit behavior. This is still in a framework where we look at the sequence of epidemic models. So now going back a little, so R0 and the Malthusian parameter, so R0 and alpha, they are usually introduced in homogeneously mixing population where everybody can contact everybody contacts everybody else at the same rate, independently of one another. And if population allows for branching process of approximation, then, which is the case in a large homogeneous mixing population, then R0 and alpha can be defined. Now in this talk I will mainly consider configuration model networks. If you know what it is, it's nice. If you don't know yet, don't worry too much. I will explain a little bit more about it as well. So one thing I have to say, epidemics on branching process, on configuration model networks have been studied very much. Again, I don't know about any real-life network which is vaguely similar to a configuration model network. It's just because we can study this epidemic model that we do so and try to extend it to more general models. But what is the most important message of the paper we wrote is that in general population structure is hard to describe. Think of a sexually transmitted disease. Now, it's clear what the contact, well, it's more or less clear what the contact is by which the epidemic spreads. Often, sociologists have some idea about what the distribution is of how many contacts people have and what the distribution is of the number of contacts people have per year and so on, the number of partners per year and all those kind of things. However, how those contacts match and so on, we have no clue about. Like, it's often possible in a questionnaire to ask how many partners did you have over the last year. Well, there are some ways to get around people lying and get those information, but it's often quite sensitive to ask whom did you have contact with. So that information is usually not available. And even the degree distribution, so how many partners somebody has. It's, well, we have an idea about it, but it's not very precise. So, in general, this population structure is hard to describe. So, we analyze what will happen if we ignore this population structure. So remember, we are not as the holy grail we are after. We often know alpha because that we can estimate from the data. So what we are going to study is how does R0 relate to alpha in a homogeneous mixing population? How does it relate to alpha on a configuration model or in other network models? or actually in other structured population models, and see how sensitive this estimate of R0 based on alpha is on the actual population structure. Okay, so now we go to the branching processes. This is we are in a mathematics institute, so I can show some mathematics here. So let Xi be a counting process, denoting the random number of daughters a woman has before age t, and mu t is the expectation of the number of daughters a woman has up to time t. And of course, this will be interpreted as the number of individuals infected by an individual which itself was infected t time units ago. Now, the key parameters in the branching process are the offspring mean, R0, which is this integral mu dt, which can be seen as just mu t, and the Malthusian parameter, which we know from the theory of branching process that it solves this equation. This can be found in the book by Pieter Trapman, but I think it can be found in any book on branching processes. And this all goes well when alpha, or when actually we have a supercritical branching process, then this alpha is well defined. So if R0 is larger than 1, this will cause no problem. Let I be a random variable with density f, I of t, and conditioned on I, let Xi t be a Poisson process with mean measure lambda times indicator of t less than I. So what does this mean? During I will be the infectious period, so the period that a person is infectious, and or the infectious lifetime if you want. And during the infectious period, an individual infects other individuals according to a homogeneous Poisson process with mean measure lambda, and it stops being infectious as soon as the infectious period is over. So this means that as long as you're still in the infectious period, your rate of infection is lambda, afterwards it's 0. So remember, this I is actually random, so the mu of dt is lambda times the probability that the infectious period is still going on, and this dt we have because we are looking at the infinitesimal rate, and R0 can be written as the integral of mu dt, and that is lambda times the expectation of the infectious period, which makes kind of sense. You have an expected duration of your infectious period of this expectation of I, and during that infectious period you infect at rate lambda. Now similarly, you can compute alpha, or actually you can find a relation for alpha. So we know that that alpha satisfies this equation. Now mu dt is lambda times this probability times dt, and we can compute this or write this as lambda over alpha times 1 minus the expectation of e to the minus alpha I. Some manipulation will lead to this, and this is lambda over alpha times 1 minus the Laplace transform of I evaluated in alpha. Now, you can already see that there is often not a closed form for alpha, because this Laplace transform is often not too nice. So taking an inverse of the Laplace transform is even harder in this sense. So however, in some cases we can do something. So if we have a large homogeneous mixing population, then branching process work immediately. So if the infectious period distribution is distributed as y, and contacts are modeled by Poisson process with rate, well, lambda hom will be of homogeneous divided by n. So every pair of individuals in a population of size n contacts according to an independent Poisson processes at rate lambda divided by n. So every individual itself, because there are n minus 1 other individuals in the population, make contacts at rate lambda times n minus 1 divided by n, so roughly lambda. So the R naught in this case is actually lambda times the expected infectious period. So you can interpret this that if you are at the start of an epidemic, not many people are infected yet, you homogeneously mix, then basically all of your contacts will be with individuals which were not affected before by the epidemic. This also works for, this is the same kind of idea you use for branching process approximations in Edwards-Rainey graphs, for example. And you can make it precise in exactly the same way. Okay. Alpha also solves this equation here, and we derived this before. Now, if I is exponentially distributed with parameter gamma, then R naught is lambda divided by gamma, and alpha is lambda minus gamma. Well, it takes some time to compute this, or it's not too hard. So this lambda we often don't know. This gamma, how long is somebody infectious on average? Well, there we can get some data on, and just pick some sick people from the street and do use the data you have on them. But how infectious somebody is, that's harder to assess. So we want to write R naught in terms of alpha, which we can estimate from our data, and gamma, which we can estimate by picking the random individuals, well, perhaps not from the street, but from the clinic or from the hospital. Yeah?
Is the exponential assumption reasonable in some cases? No.
There are some cases in which it is reasonable. I've seen talks where people try to defend that they use something else than exponential. They, for example, use a fixed infectious period instead of an exponential one. To be honest, a fixed infectious period is usually more reasonable than the exponential one. But because most epidemiology originally was written in terms of differential equations, this exponential distribution became kind of the natural thing to look at. And now I'm lying as well. This is just something nice to say about this. The seminal paper for epidemics is a paper by Cormack and McKendrick, which was way more general than using the exponential distribution. There are papers written which are called a generalized Cormack-McKendrick model, which is actually a special case of the original papers by Cormack and McKendrick.
Perfect.
But yeah, the exponential distribution is mostly for mathematical convenience.
Intuitively, if you picked up something with a heavier tail, I guess that would introduce at least more variability,
Yeah.
more chance of spreading somehow, but maybe it make it impossible to compute anything. Probably.
Well, I will have a look at it. We will have a look at it later. But actually, for the infectious period distribution, often the tail is actually lighter than the exponential.
Like you were saying about a fixed, so that there might be very little variability.
Yeah. Well, perhaps for sexually transmitted diseases, I don't know, and tuberculosis perhaps is also an exception. But many of the diseases like measles, influenza, it's closer to, or it has a lower variance than exponential.
Thank
you. Okay, networks, that's what it's all about, so let's go to that. So, we have we look at the epidemic in a configuration model. So we have assume that we have a network of n vertices. We look at the following configuration model, one of the two ways, or one of the probably more ways to define it. This one is nice for our purposes. Assign IID degrees to the vertices. Perhaps taken from a questionnaire on sexually transmitted diseases. How many partners did you have in the past 10 years? Then choose one network with the obtained degree sequence uniformly at random. This network is nice if at least the variance of the degree is finite. People are even doubting whether this is the case for sexual networks, but let's assume that it is the case. Now, this configuration model can be constructed in a nice way by basically for every individual you have assigned a degree here. You represent those degrees by stubs or half edges, and then you uniformly pair up those half edges. This gives you a graph which is uniformly among all chosen among all graphs with that degree distribution. Apart from that, there are some imperfections of parallel edges. So some individuals might have two edges between them, or there might be some self loops in this network, but we can ignore that. I think Svante wrote some very precise conditions on why we can ignore, when we can ignore it, and why we can ignore it. So the mean degree, well, is obviously the expectation of this random variable by which we choose the degree distribution. However, that is not important. As Fredrik Liljeroos, a sociologist from Stockholm, once put it, in real networks or in sexual networks, in expectation, your partner has more partners than you have. So that's always the case. So if you have a hermit, if he gets infected, then, well, he cannot infect it to anybody else, but the chance that the hermit gets infected by infectious disease is basically zero, because the person has nobody to contact. Well, if you have a very active person, in whatever way, that person is way more likely to attract the disease, or to get the disease, and then also way more likely to spread it further. Well, by the construction of the configuration model, you can see that it actually, that we need to look at a size biased, a proportional size biased distribution. to be relevant for the spread of this disease. But in anyway, the relevant parameter is this kappa, which is the expectation of the second, or it's the second moment of the degree distribution divided by the expectation of the degree distribution. And then we have a -1. So somebody who gets infected itself has an expected degree of this form. But when you get infected by someone, then the person who infected you was infectious itself. So if you're talking about a disease which gives lifelong immunity, which we will be talking about, then there is one of your partners, if you get infected, which is no longer susceptible, right? The person who infected you. So because of that, there is this -1 term here. So somebody who gets infected has on average this number of partners, and one of those partners is no longer infectious, but the others are also susceptible in the start of an epidemic by the construction of the configuration model. Now we assume that an infected individual is infectious for period I, which is a random variable again, during which it contacts every neighbor independently according to one process with rate lambda net in this case. So now we no longer have that somebody infects globally at rate lambda, but every person infects other persons at rate, a given other person at rate lambda net. Actually, if you look at sociological data for sexually transmitted diseases, this is not realistic. Turns out that somebody who has many contacts, many partners, often has less activity per partner, and somebody who has only one partner has way more contacts with that one partner than someone who has many partners has with each of the partners separately. So that's another unrealistic feature of this network, and actually we are now trying to get around or to model a bit more on that dependence between the number of contacts per partner and the number of partners somebody has. Now, if an individual has one susceptible neighbor at the start of its infectious period, then the expected number of, or the expected rate of infection at time t is lambda times the probability that at time t you didn't infect yet times the probability that at time t you're still infectious. Now, if you have k partners, then we just multiply this expected number of infections by k. So we get the same term times k, because every of the susceptible partners you infect with this probability, and expectations are additive. So this or linear. So this leads that mu dt is actually kappa times this term here, and kappa is the expected number of susceptible partners an individual has, which itself is infected. So we have a term for mu dt here, and that gives us enough information to compute R naught, which is just integral from 0 to infinity of mu dt, which will give you this term in the end, and a relation for alpha, which is 1 times e to the minus alpha t times this same term actually. Why I wrote it in this way, I don't know. So we get a term for R naught and an implicit equation for alpha. And we can then write or divide this one by this R naught net, and we get something like 1 divided by R naught on this configuration model network can be written in this way. But remember, this lambda we often don't know much about. So, but remember what our goal was. What if we don't know anything about the population? What if we don't know anything about the network? And we just assume that we have a homogeneous mixing population. Then from our alpha we can divide we can estimate R naught. And how would this relate to the real R naught? In terms of alpha, and preferably not lambda, but yeah, we have to write something. So we can compute R naught homogeneous divided by R naught net, which has this terrible expression, which I I'm not going to read out now. But what is important is that we have here 1 minus this Laplace transform divided by some term times the expected infectious period, and here we have the separate terms of the same, two terms of the same form, basically. Laplace transform evaluated in alpha plus lambda, and here it's the Laplace transform in alpha divided by some alpha, and the 1 minus Laplace transform in lambda divided by lambda. So the terms are all nice. Now a nice observation. If lambda is a Laplace transform of a positive random variable x, then this 1 minus lambda divided by 1 minus the Laplace transform of, so if we have this phi is the Laplace transform of positive random variable x, then 1 minus phi divided by theta times the expectation of this x is the Laplace transform of a uniform point on the random interval 0, x bar, where x bar is the size biased random variable of x. Well, we can deduce this, but it's very nice because this gives us that this here, those terms here itself are Laplace transforms itself. Now the log of a Laplace transform of a positive random variable is convex. Some theory on that. And we know that 1 minus this Laplace transform of I evaluated in x divided by x converges to the expectation of y. So if we look at this top term, if this alpha plus y goes to 0, then this whole thing converges to 1. As x goes to 0. And well, here I skip some steps, but from this convexity of the log we can deduce that indeed this numerator is larger or equal than the denominator and numerator. So in this case R naught homogeneous divided by R naught net is larger than 1. So what does it mean? That if we ignore the network structure, we know our alpha, we try to estimate R naught based on homogeneous mixing, what public health officials do anyway. Then they estimate an R naught which is too high. Now, it's not, so there is a bias towards estimating too high a number. That means that if you want to control an epidemic, there is a bias to buying too much vaccine. Well, that's actually good news, right? So if we don't know the network structure, well, assuming that it's a configuration model, which is often not, and we estimate R naught, we ignore the network structure, then we estimate too high in R naught and we take too much control measures. But since it's about infectious diseases, we estimate basically a worst case scenario, so that's good. Now,
does the network just add restrictions on the infectiousness or whatever? It's not a big surprise.
no, but it also has the same restrictions on the Malthusian parameter. So the network influences estimate of R naught. So it has restrictions on the how many individuals somebody can infect. But it also has restrictions on how fast an epidemic can spread. So, to me at least, it was not completely natural, or actually I couldn't predict this beforehand.
Without understanding all the details, I thought that the network just adds restrictions, so there will be a slower...
It does.
I don't know.
Now, it is a very good question actually. The network adds restrictions on the spread, but that spread adds those restrictions on the spread in terms of generations, but also on the spread in real time. And we observe that real-time spread, and we want to deduce something about the generation type of spread. So what we observe is also restricted by the network. So this result actually holds more general also if we have a random latent period. And also if the infectivity during the infectious period is constant but random, so different individuals have different infectivities. It doesn't hold in full generality, but it holds for all models I'm aware of ever studied in literature, apart from that one model we brought up to make a counterexample. Now, the very special case, which is again not realistic but is the most studied model, if this infectious period is exponential with parameter gamma, then the Laplace transform is given by gamma divided by gamma plus x, and R naught homogeneous divided by R naught net is given by this here, and the equation for the Laplace transform for the Malthusian parameter in the network is given by here. So we can deduce that lambda is gamma plus alpha divided by kappa minus 1, and the R naught homogeneous divided by R naught net is kappa plus alpha divided by gamma divided by kappa, or we can write this as 1 plus alpha divided by gamma plus kappa.
Excuse me, which one was kappa? I forgot now.
Kappa is what from the excess degree in the network.
Yes.
So kappa we often don't know because it's a parameter from the network.
But that's the only parameter of the network that appears in your finding formula.
Yeah, that's true.
Average degree, yes.
But so we can see this as 1 plus alpha divided by gamma times kappa. And for many networks, for example, if you think of the spread of sexual networks, the average degree of the number of average of the number of partners people have is pretty low. So perhaps on average in a population of people between 15 and 45 or 55, this number might be 2 or so over the last year, or even less. However, if you look at the second moment, which is most decisive for what kappa is, well, this number is usually estimated to be high. This kappa, well, can be run into the 30s, 40s, or even higher. So this R naught homogeneous divided by the R naught of the network is often pretty close to 1, which is what we want. So taking the homogeneous mixing assumption on a network model means that we overestimate R naught, but we overestimate not too high. So then the economists are also happy. We buy too much vaccine, which is good for public health, but not way too much. Now, and here, coming back to the question, what if we don't have an exponential distribution, but we have a gamma distribution with different variances? Well, the gamma distribution has mean 1, exponential would have a variance 1 as well, but here we look at 3, 1, 1/3 and 0. Well, we see that if we have a very large alpha, then we will overestimate R naught quite a bit if the variance is large. But R naught in this case is alpha plus 1. So if we have an R naught of 11 and the variance of the infectious period is very large, then we, well, don't do a very good job in estimating R naught. However, for most relevant diseases, R naught is actually quite a bit lower than 11. When I was doing my PhD, the standard joke was, well, somebody asked for R naught, let's give expert opinion of 3. That's usually more or less correct. Actually, for flu, it's more likely between 1 and 2. And R naught for 11, well, you find that in some childhood diseases. But then again, there the variance is usually pretty small, and then the overestimation factor is not too bad either. Now we have looked at epidemics. I don't have much time, so I give here just the gist of what we did, or what we further did. Also, here Jaco Wellinga came in from the Public Health Institute. He had a nice data set on multi-type or age stratified populations and who contacts whom there. There is, I now forgot what the name of that study is, in which he was involved. It's a European-wide or it's extended to European-wide study on whom contacts whom, and then you see that children contact each other, or people in the same age group usually have contacts with each other. But then also the group of 0 to 6 years has much contact with the group of around 30-year-old people contacting their parents, and then there is a contact with 0 to 6 years and the 60-year-olds, the children with their grandparents, and so on. Now you can look at this kind of model, multi-type models where you have a finite number of age groups, or well, perhaps groups based on education or whatsoever. And there we get something which is actually way nicer. If we ignore this multi-type structure, but we still assume that in every group we have there are many individuals, then actually we get that if we know alpha and the infectious period distribution, and we ignore this multi-type structure, then our R0 estimate is exact. Now, I think when Tom Britton presented this this result some years ago at in Göteborg at ECMTB meeting, there was Ellen Bake in the audience, who after some further questions said that this was not too surprising. I think after she explained to me why it's not too surprising, I agree, but it took some explanation. Actually, this result was already known by Diekman, Ode Diekman, Mats Gillenberg, Hans Metz, and Horst Thieme in a paper from the 80s, I think, where this paper was, I think it was a 50-page paper, and it was written in some corollary at page 30. It was a pretty technical paper, and they didn't bother to mention this result as a main result, but I think it's a pretty nice result, that if you ignore a multi-type structure then, and you know alpha, then your R0 estimate is pretty good. Then in parallel work, Frank, Lorenzo Pellis, and I worked on a similar question for epidemics among households. So there people are living in households, and they contact within the household at a higher rate, but people also make global contact according to homogeneous mixing assumption at a lower rate. And it is possible to define a sensible R0 here, and to find a homogeneously mixing needed vaccination coverage. And although not generally true in most serious models, if you assume homogeneous mixing, while in reality the epidemic is spreading amongst households, you will still buy too much vaccine. But downside here, in this particular case, you might buy way too much vaccine. Now, finally, how does this all behave on empirical networks? Now, as I said, empirical networks are hard to obtain. Like, we want to know how sexually transmitted disease spreads. We have no clue about that sexually transmitted network. So what we did, we went on the Stanford network data set. We thought that collaboration in condensed matter physics is a good approximation on how people behave sexually, and we spread an epidemic on this particular network. So we did this, I think, 1,000 times. In this particular case, we simulate a network, so we know exactly whom infected whom in the simulation, so we can estimate R0 based on that. We actually also know exactly when the infection took place. So we can base an R0 estimate on the epidemic growth rate on this real time, and assuming homogeneous mixing, which it's not, because we are using this condensed matter physics collaboration network. And we see that, well, this is the line in which the two estimates would be the same, that in most of the cases we will overestimate when we base our estimate on alpha. Most of the points are below this line here. And here we have some histogram of where our estimates lie if we look at the ratio of the two R0s. And for this particular network, we have no clue what the real R0 should be. So we have to estimate R0 in some way, and neither of them is the correct way, but probably R0 based on the whom infected whom is the best way to estimate it. So we see that we do, even on those empirical networks, pretty good, and we tested it on some other networks as well, and yeah, it was pretty good there as well. Only Facebook was a bit out, because it was actually what we had on Facebook was too small. Yeah.
So you're keeping the network as observed and resimulating infections,
Yeah.
or you're taking a configuration model whose degree structure is matched to the... You're not doing the latter.
No, we take the empirical network as it is. So it has also some... A problem with many networks is that there are those group structures, not only triangles, but also groups of cliques, overlapping cliques, which are preserved in this simulation. And also every time we sampled as an initial case someone else. So I think we did the right thing in simulation here. But so yeah, so the message is that all that work I did over the past 10 years was not that useful, because we can ignore it and we get a pretty good estimate anyway. However, this is only restricted to the initial phase of an epidemic, and still I think we did some nice mathematics, which apart from its application is useful as well. So thank you all.
Okay, well, we have a few minutes for questions. Anyone? Maybe I'll start. I was wondering, Frank was talking about the size of the actual epidemic. So you say large epidemics, and you mentioned R0, but that's so. What? Depending on the network structure, how large are your epidemics going to be?
That's actually very dependent on the network structure.
Exactly.
Of course, yeah. So on that respect, our previous work was useful. On the other hand, if an epidemic is bad, so it kills people, then all those models we use for epidemics is assuming that the environment stays the same during the epidemic. And that is not going to happen if something like Spanish flu outbreak will occur again. So we can say then something about assuming that we do nothing, and then it will be this bad. If we take measures, then it might be a little less bad, and we can show how bad it is. And also other properties of epidemics which public health officials are very much interested in is how many hospitals beds do we need to deal with a big outbreak. Well, I haven't touched that in my research yet. It's a very interesting question. For that, the network structure is probably also important.
Other questions? Yep.
It's not really my expertise, but no, you were talking about K different types of individuals.
Yeah.
And you mentioned different age groups. So I was wondering if age, so you can include in the model covariates like age.
Yeah.
The parametric, like rather than dividing into groups.
Well, what we still need in our assumption is that every group, so we want to have a finite number of groups, because for this model the assumption is that all groups grow very big. So we don't not only need that the population size becomes big, but every single group should have many individuals in it. So we cannot deal with a continuum of ages in this case.
Okay. Anyone? Another question? If not, then maybe if you have more questions, you can obviously ask over tea, which is now. But let's thank Pieter again.